Ah, Good morning, everyone. Let's discuss a topic in computational logic, computational tree logic. Me and my friends Hanuman, Ishwar Manikanta, and Akash are going to discuss about this now. Computational tree logic is an indeed extension of a propositional logic designed for the reasoning about the systems with the temporal aspects. It is a particularly useful for specifying and verifying properties of system that evolves over the time, such as hardware circuits, software programs, and even complex processes in various domains. Computational logic is often used in the model checking and formal method of for the system verification. Tree structure. The tree structure of computational tree logic, the system behaviors is represented as a tree structure. This tree structure starts from a node, root node, which represents the initial state of the system and branches out as you move through time. Each node in the system corresponded to possible state of the system at a specific time. Decisional branch points. As you move along with the branches of the tree, you encounter various branches points. At these points, decisions can be made or different possibilities can be explored. These branching points typically represent choices or undeterministic events. Temporal aspects. Computational tree logic excellently consider the temporal aspects of a system. It allows us to express properties and conditions that must hold at a specific point in the future. For example, you can specify the certain condition while always cold. Example, it will always be sunny, or that condition will be eventually be true. Example, the system will be eventually reach a state which is not completed a task. Non-determinism. Computational tree logic acknowledges that systems can be non-deterministic. This means that at certain point in a tree, there may be a multiple possibilities, outcomes, or transactions. Verification model checking. Computational tree logic is commonly used for the formal verification, where you define the properties or specifications about the system, and then a model checker verifies whether these properties holds in the system behavior. Now, this is the syntax of the computational tree logic. It is defined. This formula is defined intuitively via the Backus Nose form as done for the LTL formula. In computational tree logic, a formula is an expression that can be evaluated as either true or false. Those formulas are used to express the properties and conditions of the system as well as evolves over the time. Predicate statements. Predicate statements are fundamental components of computational tree logic. These are the expressions that can be evaluated as true as false based on the current state or conditions. They can be used in the computational tree logic to specify various properties and constraints about a system. Connectives. Computational tree logic uses the logical connectives to build the complex formulas. These connectives includes conjunction, bijection, implies, bidirectional conditions, and statements are equivalent. Special symbols. Computational tree logic introduces special symbols to express the temporal properties. These symbols includes AX for all next, EX exists next, AF for all finally, AG for all globally, EG extends globally, AU all units, etc. In summarize, computational tree logic is a formula logic system used for the specifying and verifying temporal properties of a system. It provides a rich set of logical operations and temporal operations to express conditions that must hold at different points in the time. Thank you. From now, my friend will continue this.
Let's see the special symbols in CTL. Here A represents for all and inevitability. E represents at least one or possibility. And A describes criteria for all paths. E describes criteria for at least one path. And X represents next state or node. F represents some future state or node. G represents globally or universally. Different combinations of these operators define validity. And here another one, U represents until.
Now moving to the validating CTL formulas. Validating CTL formulas tree comparison is an essential process when working with model checking, and formula verification of software and hardware systems. There are 5 steps involved in this validating CTL formulas. First one is draw parse tree. Parse tree is a graphical representation of how a CTL formula is structured. Now, second step is to follow backup norm form, which is a BNF structure. CTL formulas other to the form, which defines how the elements of the how can be combined. Follow the structure when the constructing or evaluating CTL formulas to ensure they conform to the language's syntax rules. Third is evaluate subformulas in the tree. Before accessing the validity of the entire CTL formula, evaluate each subformula recursively. For example, if you have an AND operator, evaluate the left and right subformulas to determine if they are valid. Fourth one is check the validity of each operator connected. CTL provides various operators and connectives such as AND or NOT, AX, EX, AG, EG, etc. Whereas AX, EX, AG, EG, etc. are the special symbols. Now, fifth one is ensure well-formed and valid formulas for CTL. Well-formed refers to the syntactic correctness of a CTL formula. It should conform to the VNS structure. There is nothing. Now, moving to the example of our computational tree logic. Here, expression is given for which and P and Q is a primary priority symbol for which we need to construct a parse tree first. So P and Q is constructed first, then along with EX, the right hand side non-negation P is constructed along with EU, whereas E and U are combined, for which U is a binary symbol. Now, moving to the semantic entailment in CTL. So these are the given meanings of the special symbols AG, EG, AF, and EF. AG, all paths globally satisfy the condition, for which we already have discussed that A is the along path, along all paths, whereas U is until. So combining A and G will get along all paths globally satisfy the condition. So whereas EG is at least one path and G is globally. Now combining E and G will get at least one path in the future satisfies the condition. Similarly, AF is all paths should have the condition in the future, and EF at least one path should have the condition in the future. Now my Hanuman friend will explain the example for CTL validity.
Let's discuss some examples of the CTL validity. Yeah, let's discuss this example. In this, we have a condition called EF5, which means, according to our special symbols, E is along at least one path, having globally phi as a label. See, let us check in the past tree. We had phi at least one future state. So hence it follows the given condition. And next example, let's consider this example, which is EG5, which means along at least one path globally, we must have phi as a label. As we can check here, in at least from one path, from starting node to the last node, we are having phi. So it's semantically entitled with the given model. And the last model, here it AG5, which means along all the paths globally, we must have phi as a label. According to our past tree, phi is being present globally in all nodes as a label. Hence, this follows the semantical entailment. Thank you for giving this opportunity.